Hello everyone, welcome to this lecture video tutorial in Calculus 3. Enjoy learning. Hello everyone, in this lecture video we will be discussing differentiation and integration of power series. So this is lesson number 8. So uh, we have here a theorem. It says that a power series, we discussed that in lesson number 7, defines a function where the domain is the interval of convergence. So we can write it in this form with r is greater than 0. So remember that this is a theorem, so it requires that our radius of convergence is greater than 0. Hence, the function f is differentiable and continuous there. Thus, the derivative and antiderivative exist, and they are the following. Number 1, number 2. This is for differentiation, and this is for the integration. And we have a note here that the radius of convergence of the series obtained by differentiating. So after you differentiate, so this is your function, your power series after differentiating or integrating, it is the same as that of the original power series, the radius of convergence. However, the interval of convergence may differ as a result of the behavior at the endpoints. Okay, remember that it will matter the 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 original series may not have the same interval of convergence when you get the derivative and the antiderivative of the original power series. So be careful, you have to test the endpoints. Okay, so before we have some example, let's have an illustration here. So I know that you are familiar with the geometric series. Okay, so if you recall your geometric series, let's say recall here. So I will paste it here. So I'm going to find it in my laptop first. Okay, so this is the definition of the geometric series. So we will start our discussion in this series. So remember this form. This is the geometric series. Okay, and we know that the n partial sum is denoted by this form. Okay, and the series, this series converges to the sum a over 1 minus r. Okay, and diverges for this one. Okay, diverges if the absolute value of r is less than 1, and they converges for absolute value of r less than 1, and diverges for absolute value of r which is greater than or equal to 1. Okay, so what we will do here, is that we will start we will start at this series, this one. Remember that this series start at n is equal to 1, so we will start at n is equal to 0. Okay, let's derive, because our goal is to have a power series, mean to say we have an x something. So what we will do here, that this, in order for this one to converge, our r here is less than 1. Okay, so please remember that. sorry, this is r starts from sorry from 1. Okay, from 1 here. So we will start we will derive the power series where our n starts from 0. So okay, this implies that summation of a r to the n minus 1, multiply both sides uh, by what you call this one, by r. Okay, multiply both sides by r. This becomes multiply both sides by r. Okay, so this will become a to the r positive infinity ar 1 minus r. Okay, so this implies that summation of ar to the n, where n starts from 0 to positive infinity, this can be written as a r to the 0 plus summation of ar to the n, or n starts from this is r to the n. Okay, 1 to positive infinity. Okay, and we know that this is 1, positive 1. So what will happen here is this is ar. This term here is this one. Okay, this is ar over 1 minus r. So simplify, get the LCD. 1 minus r. This is a times 1 minus r plus ar. And then if you simplify this will become a minus ar plus ar over 1 minus r. Okay, so this is 0. So it will be, notice that the formula is the same as that of the series where n starts from 1. Okay, so if r is less than 1, absolute value, so we derive that our series, this one here, no, that not the series, the geometric series, so this geometric series is have a sum which is equal to a over 1 minus r for r which is less than, or absolute value of r is less than 1. Okay, so what we will do here is we have to replace no, not replace, but we have to let a is equal to 1 and r is equal to x. Okay, then this will become a summation of our a is 1, so this will become x to the n, where n starts from 0 to positive infinity, and this is equal to 1 over 1 minus x if this one. Okay, so power series in x, and we know that this is a function, so we can write, so this implies that we can write the series, this one, x to the n, where n starts from 0 to positive infinity, to be equal to 1 minus x, as long as your x is less than, absolute value of x is less than 1. Okay, so now we can do differentiation and integration for this. Okay, but before that, uh, by the way, if you expand this expression here, this is equal to 1 plus x squared plus x cubed up to x to the n plus dot, which is equal to 1 over 1 minus x. Okay, so from here, if we replace, okay, if we replace let's try to play the given series, the geometric series. If we replace x by negative x, this will become, the series becomes this form, negative x to the n, where n starts from 0 to positive infinity, and we can simplify this as negative 1 to the n, sorry, the n starts from 0 to positive infinity, x to the n. Okay, and this is equal to, replace our x here by negative x, so we have 1 over 1 minus negative x, so this will become 1 over 1 plus x. Of course, if we again replace our x here by negative x, so we can simplify this as this form. Okay, we can write this one by negative 1 times, sorry, what happened, okay, it's something wrong. Okay, can write it in this form, and we know that this is equal to that one. Okay, absolute value of negative 1 is of course negative 1 is 1. Okay, so if we replace our x by negative x, we have this form. Okay, so meaning to say, this expression here is, the sum is equal to this one. Okay, that one. Okay, again, if we, let's try this color, let's say black. If we replace by replace x by example x squared, that one, what will happen here, we will have this form, x squared to the n starts from 0 to positive infinity, so this is summation of x to the 2n, so n times 2 is 2n, n starts from 0 to positive infinity. So what will happen here is, this is equal to 1 over 1 minus x squared. Okay, so if, of course, if you replace x by x squared, this will become in this form, and we know that this form here is can we simplify this one? We can write it as this one. Okay, x that one. Okay, sorry, there's a point somewhere. Okay, we have to wait, just wait something. Okay, this one, and this is equal to absolute value of x times absolute value of x. Okay, and then this is equal to absolute value of x to the power of 2. Okay, but since this is less than 1, so we can take the square root both sides. Okay, that one. So again, this is absolute value of x, which is less than 1. So we can simplify this as absolute value of x less than 1. Okay, so that's the series summation of x to the 2n power series, where n starts from 0 to positive infinity, is equal to this form here, 1 over 1 minus x squared. Of course, your x is less than, absolute value of x is less than or equal to 1, which is equivalent to, if you simplify this, you can write this one as negative x, no, sorry. You can write this as, again, we have to wait, negative 1 less than x less than 1. Okay? Less than x less than 1. This is in your algebra. So let's have one more. Let's replace x by, example, if you have negative x squared. Okay, if you replace x by negative x squared, this will become negative x squared to the power of n, where n starts from 0 to positive infinity. Okay, and if you simplify this, you can have negative 1 to the n, sorry, to the n, x to the 2n, where n starts from 0 to positive infinity. And this is equivalent to 1 minus negative quantity negative x squared. And if you simplify this, we have, this is 1 plus x squared. Okay, of course this is less than 1. Again, if you simplify this, replace x here, or x here, replace in the above by negative x squared, and if you simplify it, it will become like this. Okay, so what's the point of replacing x something by other expression? Okay, let me put a note here. Let's try this purple color. Let's have a note in this discussion. We will learn that other interesting series can be obtained from those like the above. If above by differentiation and integration. Okay, so please remember that in those method that we discussed above, we can obtain other interesting series using the idea of differentiation and integration of the power series. So let's have an example here. Okay, example, let's try this black color here. Example. Okay, so obtain a power series of this one, sorry, I forgot, maybe I remember now the problem. So I guess I have to power series representation of 1 over 1 minus the quantity. Okay, so let's have a solution here. So let's get a power series representation of this expression here. Okay, remember that in our discussion above, this one, uh, this series here, or geometric series, remember that if we write this one as a exponential form, this is equal to something like, 1 minus x to the power of negative 1. Okay, so in order for this expression to have a power of 2, then what we will do is to get the derivative. Okay, because if you get the integration, then the idea of differentiation is you have to add 1 to the numerator, so this will become 0. So we will use this expression, this one, summation of x to the n, where n starts from 0 to positive infinity, which is equal to 1 over 1 minus x, to get the power series representation of our problem. Okay, this one. So okay, so sorry, what happened? Okay, so let's start uh, at this series. Okay, x to the n, where n starts from 0 to positive infinity, which is equal to 1 over 1 minus x. Of course, if x is less than 1. Okay, so we will have to get the derivative. Okay, so but first let's have express this as a sum. So this is 1. Can we have another color here? Let's say blue. This is expand 1 plus x squared plus x cubed plus x to the 4 plus and so on up to x to the n plus dot dot dot. This is equal to 1 minus x to the power of negative 1. Okay, so get the derivative. Okay, get the derivative of the other side, this expression, the left hand side expression, and on the other side also, x plus x squared plus x cubed plus x to the 4 up to x to the n plus, okay, 1 minus x to the negative 1, that one. Okay, so the answer is this is 0. First we have, say, this color and change this one. Okay, this is 0 plus 1 plus 2x plus 3x squared plus 4x cubed plus dot dot dot. This is nx to the n minus 1. And on the other side, this is negative 1, or negative of 1 minus x to the power of negative 2. Okay, then we have to use chain rule. The derivative of this one here is 0 minus 1. Okay, so simplify, and if we simplify the right hand side, this is equal to 1. Now this is positive. Now we have negative times negative, so we have positive. Then we have to bring down a to the denominator. This is that one. Okay, and this side here we can write it as a sum. Okay, summation. So what's the summation form? And we know that this form here is our n term, x to the n minus 1. So our n must start from what? So if this is 0, this is, of course, this is positive infinity. If this is 0, we have 0 times an expression here is 0. Okay, so we have a 0 here. This one, when n is equal to 1, we have 1. Okay, when n is equal to 1, we have 1 times x to the 1 minus 1 is x to the 0. Okay, so we have 1 here. Okay, and then if n is equal to 2, we have 2 here, and we have x to the 2 minus 1, we have this one. So we will start at uh, n is equal to 0. Okay, so this is our power. This is the power series representation of 1 over 1 minus x squared. Okay, so this is it. Okay, so that's how you are going to obtain a power series representation. So make sure that you have a known power series, like the geometric series or maybe the harmonic series, the well-known series that we discussed in uh, previous lesson. Okay, so let's try another example. Okay, so let's have this example here. Just and notice that the problem is you are going to get the power series representation of 1 over 1 minus x squared. So you have to check it yourself if this series here have the same what they call this one, the same radius of convergence and interval of convergence. So that's your assignment or problem, but you are not going to pass that one. Okay, let's have another example here. So example number 2. Show that e to the x is equal to the summation of x to the n over n factorial, where n starts from 0 to positive infinity for all x. Okay, so meaning to say we know that the domain of the exponential function is the set of real numbers. Okay, so let's try to show that indeed this series here is equal to this function. Okay, solution. Let's try this color here, solution. Okay, first is let's get we have to let f of x and then get the derivative. Okay, if not, and get the differentiation. Anyway, x to the n over n factorial, where n starts from 0 to positive infinity. Okay, so get the derivative. Maybe let's have an example for integration later. So for the derivative of this one is we know that if we expand, okay, if we expand this, the expansion of this series is when n is equal to 0, so we have x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x to the 2 over 2 factorial. This is x to the 3 over, let's have more terms, x to the n over n factorial. This is much easier if we expand this one and get the derivative. Okay, so this is 1. 0 factorial is 1, x to the 0 is 1, so we have 1 over 1, so this is 0. Okay, the derivative is 0. For this one, this is 1. And here we have uh, 0. Let's try to write it in this form. 2x over 2 factorial plus 3x squared over 3 factorial and so on, and we can write this one as this. The derivative of this n term is this one as that. Okay, so if we are going to write it in the summation notation form, so we can write it as this one. Okay, this copy this n term and x to the n. Sorry, this is minus 1. Okay, minus 1 over n factorial. N starts from, okay, let's play. So when n is equal to 0, we have 0 factorial. We have 0 factorial here. 0 times, no. 0 is, when n is equal to 0, this is, there's something wrong, because what we will have here is we have x to the negative 1. Okay, so our n must not be equal to, must not start at n is equal to 0. Okay, so maybe it should start at 1. So let's write 1 here. 1 factorial we have here. 1 x to the 0, you have correct. When n is equal to 2, we have 2 factorial 2. So I guess this is the right one. Okay, so our f prime of x is equal to that one. Okay, so what we will do here is we have to simplify. Maybe we can write it in this form. Summation of our, maybe we will have this expression there. Let's try to write it as, we have n x to the n minus 1 over n times n minus 1 factorial. Okay, and then we can cancel out n here, so we have x to the n minus 1 over n minus 1 factorial. Okay, so this is equivalent to this form. Okay, so x to the n minus 1 over n minus 1 factorial, where n starts from 1 to positive infinity. Okay, so what we will do here is that, notice that in this expression here and the given, this one, if we replace our n minus 1 here by n, notice that it will be the same. And if you expand this one, if you expand this, it will be the same as this expression. Okay, so maybe we can write this as, not maybe, but I'm pretty sure that this can be written as, but this is not always the case. Okay, but there are problems that it is not always the case. Okay, n factorial, n starts from 0 to positive infinity. Okay, so okay, just play the expression on the right hand side and notice that it is equal to the given. Okay, so, and what will happen here is that f prime of x is equal to f of x. Okay, so this is our f of x by the given, as we notice in the expression above. Okay, and in our calculus 1, we can write this one as y prime is equal to y. and we can express as in this form. And this is a differential equation. I think this is a separable differential equation. So we can write this one as dy over y is equal to dx. Okay, then if you integrate both sides, y, this is equal to ln x. No, not ln x, ln y. Sorry. This is ln y is equal to x plus c1. Let's try c1. Okay, and then this is equal to y e to the x plus c1, and we can write it in this form, e to the x times e to the c1, and then we can write it again in this form where our capital C is e to the c1. Okay, so notice this is our f of x. Okay, f of x, c e to the x. Okay, notice if x is equal to 0, then f of 0 is equal to what happened? What is the value of our y? If x is equal to 0, our y is c e to the 0, or this is equal to c, right? Okay, and then we know that not by, okay, anyway, let's wait, but let's recall our f of x, or our f of x is this one, summation of x to the n over n factorial, n starts from 0 to positive infinity. If we replace it by 0, this will become, if you expand, this is 1 plus x over 1 factorial plus x squared over 2 factorial, and so on and so forth, x to the n over n factorial. So if you substitute, this is 1 plus 0 plus 0 plus 0 plus, and so on, 0 plus. Okay, so therefore f of 0 is equal to 1. So let's move this upward. This equation here, we will substitute it to this one, to the expression above. So this implies that c is equal to 1. Okay, substitute here. So, and this implies that our function, this implies that f of x is equal to e to the x. Okay, but our f of x is summation of x to the n over n factorial, where n starts from 0 to positive infinity. Okay, so let's try to make it more beautiful. Okay, so we have shown that e to the x is equal to this series. Okay, and we know that e to the x, the domain is the set of real numbers. Okay, so we have shown that for all x, this one, summation of x to the n over n factorial, where n starts from 0 to infinity, is equal to e to the x. But if we are not convinced, then use ratio test to show that the interval of convergence is the set of real numbers. Okay, so that's it. Let's have another problem. Let's try integration. Example for okay, before we have an example of integration of a power series, let's apply the let's apply example number 2 to this example. uh, Example number 3, obtain a power series representation of let's say e to the negative x. Okay, solution. So uh, remember that the power series representation for e to the x is this one. So let's recall e to the x is summation of x to the n over n factorial, and starts from 0 to positive infinity. Okay, and then we have to replace x. Okay, replace x. Let's try this. Let's denote this as a star. Okay, replace x by negative x in equation star. Okay, so we have e to the negative x summation of negative x to the n over n factorial, where n starts from 0 to positive infinity. And this is very easy. Simplify. This is negative 1 to the n x to the n over n factorial. N starts from 0 to positive infinity. So we are done. Okay, that's easy. So if you want to take the maybe let's try to get the what you call this one, interval, the radius and interval of convergence. So of this series here, find the interval. So interval and radius of convergence in let's say, let's try this as sharp, in sharp. Okay, so let's move up. So again, get the limit of a sub n plus 1. This is very familiar as n approaches to positive infinity. Okay, so substitute, replace n by n plus 1. So we have negative 1 to the n plus 1 x to the n plus 1 over n plus 1 factorial. Okay, then the denominator becomes this one, x to the n over n factorial, as n approaches to positive infinity. Okay, simplify. Negative 1 to the n times negative 1 times x to the n times x over n plus 1 times n factorial, and then the denominator becomes n factorial over negative 1 to the n times x to the n approaches to positive infinity. Okay, let's move up. So I think we can cancel out. Let's have this color here. Let's wait. This one can cancel out this one here, and also this one. Okay, so what remains is we have absolute value of negative is positive, so we have absolute value of x times the limit of 1 over n plus 1. Okay, as n approaches to positive infinity, and we know that this is 0. Okay, so this is 0, but this is less than 1. Okay, so this means that the what they call this one, the interval of convergence. Okay, therefore the interval of convergence is from negative infinity to positive infinity, and the radius of convergence is infinity. Okay, so that's it. That's how you are going to apply the idea of differentiation and integration of power series. Okay, so maybe let's have now an example for integration. So let's have this one, example number 4. Obtain a power series representation of tangent inverse x. Okay, so tangent inverse of x. So remember, so just pause for a moment and then analyze. How do we get a power series representation of tangent inverse of x? Okay, so pause for a moment and then analyze. Okay, so there is a trick here. Okay, let's try this color. Recall that in the what they call the integration formula. Okay, integration formula. Recall that integral of du over a squared plus u squared is equal to 1 over a times tangent inverse of u over a plus c. So notice here that our a here, let's try this one. Our a here is 1 and our u is x. Okay, so we can have this form, tangent inverse of x. So we have this integral notation on the left hand side. We have integral of du. So what will happen here is that on the left hand side, okay, on the this one, left hand side, this will become integral of du over 1 plus x squared. Okay, and then we will have tangent inverse of x plus c. Okay, so we will use this idea to get the what they call this one, to get the power series representation of tangent inverse x. And recall that in the geometric series we have this expression before. Recall again. Let's try this color purple. Recall again that Let's move up. Sorry, what happened? So anyway, recall in our previous discussion that if we replace remember the geometric series geometric series. Okay, summation of x to the n, where n starts from 0 to positive infinity, this is equal to 1 over 1 minus x, and this is convergent if x is less than 1. So if we what do you call this one, if we replace x by, I guess, by negative x squared. Okay, so we will have uh, summation of negative x squared to the power of n, where n starts from 0 to positive infinity, and this is equal to 1 over 1 plus x squared. Okay, if this one, I discussed this one already. So we will use this idea to get the integration, no, not integration. We will use the idea of integration of the power series to get the power series representation of tangent inverse of x. So this implies that integral of 1 over 1 plus x squared dx is equal to the integral of summation of negative 1 to the n, sorry, negative 1 to the n, x to the 2n. Okay, where n starts from 0 to positive infinity. Okay, dx. Okay. And we know that this is the left hand side is tangent inverse. Okay, this is tangent inverse of x. Okay, so we will put the c here on the other side. Okay, let's try to expand this one. This is when n is equal to 0, so we have 1 minus when n is equal to 1, we have x squared plus x to the, when n is equal to 0, 1, 2, 2, 4, minus x to the 6 plus x to the 8 minus x to the 10 plus dot up to negative 1 to the n x to the 2n plus dot. Okay, dx. Okay, let's try to integrate this one. So the integral of 1 is x minus 2x over 2 plus, this is 4, no, plus 1, we have 3. No, I guess I'm doing differentiation. I guess I am wrong. Sorry, this one is plus 1. We have x cubed over 3, that one, plus x to the 5 over 5 minus x to the 7 over 7 plus x to the 9 over 9 minus x to the 11 over 11, and so on up to, this is negative 1 to the n. We have x to the 2n plus 1 over 2n plus 1 plus dot plus c. let's try to put a C here. Okay, let's wait. Maybe we have to wait for the program to respond. Okay, so we can write C here, something plus C. Okay, so let's try to write this in the summation form. This is negative 1 to the n. This one here, the n term, this is our n term, x to the 2n plus 1 over 2n plus 1, where n starts from what? So let's try to verify. If n is equal to 0, so we have 0, 0 plus 1, we have 1, and then x to the 1, okay, we have here, and then n to the 0, we have 0 here, we have positive, so this will start at n is equal to 0. So when n is equal to 1, we have 3, 2 times 1 is 3, we have 3 here, 3, and then we have negative. Okay, so that's correct. So this is tangent inverse of x, tangent inverse of x. Okay, so now as you can see, this is the power series representation of the tangent inverse. So what we will do with the C here? Okay, so when what we will do here is when x is equal to 0, what is the geometric series that we got? This one, sorry, no, not the geometric series, I guess this one. So this one here, so when this is 0, tangent inverse of 0, and this one here, sorry, and is equal to 0 to positive infinity, so we have 0 to the 2n plus 1, so this is 2n plus 1 plus C. Okay, so what is the tangent inverse of 0? So this is 0, of course, and this one here is 0. Okay, and this is C. Okay, so therefore tangent inverse of x is the summation of negative 1 to the n, x to the 2n plus 1 over 2n plus 1, n starts from 0 to positive infinity. Okay, so to get the interval and the radius of convergence of the series, again, just use the ratio test. Okay, so I guess that's all for this discussion. Let's have an assignment here. Okay, assignment. Okay, this is your assignment for this lecture. We have 4 assignment. Okay, so that's all for this lecture. If you are new again, don't forget to subscribe to my channel by clicking that red button, subscribe button, and bell button down below. Thank you so much everyone for watching. Enjoy learning.